low pass filter. And the next one, you can get a minus 40 dB, two pole. And the last one here will be minus 60 dB per decade. That's three pole. The ideal filter you want right here. After the cutoff, you don't want any frequency, any signal. Okay? So minus 60 dB will be the best in this example. Okay? And on this one, we already done or not? Okay? We get a low pass filter. They given you R will be 1K, C will be 0.1 microfarad. And this one they're using the unity gate amplifier to build a filter. So the gain will be equal 1. Okay? So the answer we already did last time, I believe so. Gain equal 1. What's the cutoff frequency?
7.07 volts.
Cutoff frequency.
1.59.
1.59, right?
Yes, sorry.
Okay? VL after cutoff will be, is it right?
7.07 volts.
Okay? And VL at the 10 time. That's what we already done last time. Okay? Any question on this example? Okay? The next one here, example, they using what the name for the circuit. They using what? Inverting, non-inverting, follower,
Inverting.
inverting, or non-inverting.
Yes. Non-inverting.
Non-inverting. Okay? And the gain of the non-inverting will be 1 plus R2 over R1. So what AV equal? 10, right?
10, yes.
Yeah, last time, I believe we already done. Cutoff frequency, 1 over 2 pi FC, RC.
159.
159. What's the VL maximum? You want VL maximum, you take the input times the gain. Is it right?
35.
Mr. Pham,
Right.
Mr. Pham, can you stop me getting that? Got a question.
Yeah.
R2, what's the value of R2?
R2, 9K, right?
9K 1 ohm, or is it 9?
9K, 9K, oh, that's the, maybe the typo.
Okay, all right, thank you.
Okay, number 4. VLS cutoff.
$17.65.
Oh,
That scared me, bro. That scared me.
Is it a VLS cutoff? It will be 17.67. If you want to calculate the VL at the cutoff, you take the VL maximum times 0.707. and the last one will be 2.5. That means the VL at 10 FC. You want to calculate the VL at 10 FC, you take the VL maximum times 0.1.
Can you repeat the number 5 again, please?
Number 5,
Yes, please.
okay, you want to calculate the VL at the 10 times of the cutoff frequency, you take the VL maximum times 0.1.
Yeah, maximum. 0.1. Thank you.
Okay, the next will be
Sam, could you put that back real quick? I was writing something. Okay, thank you.
welcome. The next will be a high pass filter. Okay, so that's the opposite to the low pass. They will be pass any signal at higher than the cutoff frequency. Okay, so this is the cutoff frequency here. Any frequency signal higher than, they will be allowed to pass through it. Okay, less than cutoff frequency, they will be transient. So that's why they say bandwidth of the high pass filter right here. They're telling you bandwidth or pass band. And the formula to calculate cutoff frequency the same like low pass filter. Okay, now we want that to do calculation. Okay, so the gain. What is the gain for this filter? What the circuitry using for the high pass filter here? What amplifier?
Challenge 30.
For this circuitry here, what the amplifier be to build the filter?
Inverted?
Inverting, correct?
Using the negative.
Yeah, input connect to the negative. And the gain will be equal what?
1.
Will be not, right? R2 over R1. Okay? So, what is the gain equal?
Point 7.
Two point minus 2.7. Is it correct?
Yeah.
Okay. Cutoff frequency. Did we do last time? Or no?
No.
No.
No, okay, do it now. Cutoff will be equal 1 over 2 pi.
Mr. Fan, why is it negative 2.7?
Huh, now you ask me how come they equal negative?
Is it because it's going up instead of going down?
No. You have to go back with the negative inverting amplifier. What the gain for inverting amplifier? That's the formula.
R2 over R1. Yeah,
Minus,
but it's negative. It's negative. Negative R2 over R1.
Right. That's just a formula. I'm
Oh.
not make it up.
Okay.
Okay?
Is it because it's using the negative side of the wave?
Okay. Try to make sure you go to the op amp. You get inverting, non-inverting. When you see the circuitry, you have to tell me which one. This is just a formula. Input applied to the negative, that will be inverting. Input applied to positive, that means non-inverting. That is the first thing you must know. Then you have to know next one will be what is the gain. You don't have to prove it, but you have to memorize. For this gain in here will be minus RF over R1. For the non-inverting will be 1 plus RF over R1. That is the thing you must be memorized. I cannot help you out.
Hey, Mr. Pham, but I think what they're trying to understand is, even though it's the formula, why is the negative in the formula? I understand what you're saying, but that the negative is in the formula, but why is it in there? We know that negative is inverting and positive is non-inverting. But what I think what they're trying to find out, why is the negative there?
Okay.
Isn't it because it's using the negative side of the sine wave?
Now, nothing to do but that sideways. Okay. Now, on this one here, this is a VL. Right?
Right.
Okay, VL will be measured from the output to the route. And also, VL can be measured from left to this one. This also route. Right?
Right.
So the current will be flowing this way. So you get positive here, that's negative here. Okay? So VL will be basically equal minus I right?
Right.
Okay? That is the VL. And now you get the gain. AV VL divide VE. You get that?
Right.
VL will be equal minus I R2 divide V in. What V in equal?
I R1.
Time I. Right?
Right.
Yeah.
I R1. Get the AV. AV will be equal cancel I minus R2. That explains to the why they get minus.
Okay.
Okay? But I think you don't have to prove. Try to memorize the formula. Yeah, anything if you confusing, just bring it up. We try to make it clear for you guys. Now the cutoff frequency, still the same thing. 1
Yeah.
over
159.
that is the same formula. 1 to 5 RC. What you get?
159.15.
15.9.
Kilohertz.
Okay. What the V out mic?
4.05.
Yeah, if you want to calculate, you can take the gain. Times the sine wave. Okay? The gain equal to minus, however, that will be applied for DC. For AC, that minus only telling you what input output will be opposite. Okay? So the right answer will be 4.05. Okay? Not negative. Why? AC, you cannot put a negative. The negative side just telling you input output will be half phase. And the last one, VL at 1.59K. That means they lower than 10 decade. Cut off 15.9. You divide by 10. You get 1.59K. And the output, they will be down minus 20 dB. So what you get? For mine, I get 0.286.
Stefan, I'm sorry. How did we get this number again?
How? Can you repeat your question?
Yes. How did we solve number 5?
Number 5, that means the cutoff frequency changing for 1 decade. Okay? That means the output will be going to 0.1. You take the V out times 0.1.
Okay. So the VR that we have is 4.05 times 0.1. Is that what you mean?
Let's see. Number 4, what we get?
4.05.
No. Sorry. 4.05 will be number 3.
Yeah, that's maximum.
Yep. 2.86 for number 4.
Yes. Yeah, 2.86. That's right.
That number okay, that number 3.
Okay.
VL mic. That will be 4.05. Okay, number 4. That means at the cutoff frequency, they will be 2.86. And number 5 will be now to 0.1. That means 0.286.
So is it 0.1 times V out at critical frequency or
Right. That means at the cutoff.
at the cutoff times 0.1?
Right.
And not feed max.
Okay. I get the wrong one. Will be time to be mic. Okay?
It should be 0.405.
Exactly.
All right, thank you.
Thank you. 0.405. Okay, that means they take 0.1 times 4.05. Okay?
And I'm sorry, Mr. Pham, like, so the 0.1 is constant, right, in this case? Or
0. Which number you talking about? Number 3, 4, 5.
the number 5, when we multiply the V out max multiplied by 0.1, 0.1. So where did we get the 0.1 from? Is it from the formula or?
Now, you understand when they down 20 dB, that means minus 20 dB. You cannot do anything with that minus 20 dB. You cannot do any calculation. So now you have to find out what number you get at minus 20 dB. That means you can take a 20 log 0.1. So that will be minus 20. So you have to multiply by 0.1. Same thing like minus 3 dB. When you say down minus 3 dB, you cannot do anything with a minus 3 dB. Then you have to say 20 log of 0.707 equal minus 3 dB. So you want to multiply, you have to multiply with 0.707.
Okay, thank you.
Okay, now my question is, if they going down to another 10 times FC, then you have to multiply by what number? That means they go to a 40 dB, minus 40.
0.001.
0.01, not 00.
Okay.
I think if you take the log of 20 log of 0.01, you get minus 40. Okay?
Okay. Thank
Okay,
you.
on this circuitry here, they just given to you a 2 pole. I already telling you, when you get a 1R, 1C, set a 1 pole. Okay? That means the circuitry, you can get only 1R, only 1C. So that will be 1 pole. Okay? 1 pole will be going down 20 dB per decade. When you get 2C, 2R, that 2C, that 2R. So that's why they will be 2 pole. The thing is this, for this kind of the filter here, you don't care about the circuit. It's very, very hard to looking into the circuitry to tell what the name. They will be 2 pole, 3 pole, or more. No way. The thing is, basically, when you're working, and they just asking you apply input and measure what the output is supposed to be. And they telling you this will be a 2 pole, okay? Cannot memorize circuitry. I just give it to you, the circuitry, in order to explain to you how you get the 1 pole, how you get the 2 pole. Okay? And also, if you're looking into this circuitry here, can you tell me what the amplified they yield to build?
Non-inverting amplifier?
What's the name?
Non-inverting amplifier?
Exactly. Non-inverting. What is the gain?
1 plus R2 over R1.
All right. Okay. Now the next one, band pass filter. Okay, first thing you're looking into the circuitry, what the name of the amplifier?
Non-inverting amplifier.
Right, non-inverting amplifier. What is the gain?
One plus R4 over R3.
1 plus R4 over R3. That's correct. Okay. So basically, you already learned that one. What is the name for this circuit?
High pass filter?
High pass filter. Okay? Normally, when you interview, they just give you that. Asking you what is it? The answer will be, that will be output of the high pass filter. And the same for this guy here. What is it?
Low pass filter.
Okay, low pass filter. And now they combine high pass and a low pass to make the one they call a band pass. Okay? So that's why band pass they get a two cutoff frequency. One will be F low and one will be F high. Okay? Any signal with a frequency higher than F low and less than F high allowed to pass. Okay? Any signal with higher frequency than F high will be rejected after F low. So the band pass will be from F low to F high. That's what they call a band width or pass band.
Hey, Mr.
Now
Pham,
you
I have a question.
understand? Yeah.
I understand what you just said. Do the high pass and low pass, they have a bandwidth also, right?
Yeah, bandwidth for the high pass and the low pass, they only so right here. Bandwidth for the high pass here. This is the bandwidth for the low pass here.
Right. Okay, yeah, all right, thank you.
Yeah. So basically, this is
I have a question. How can you find out the bandwidth of a high pass? Which formula are we going to use?
band pass for high pass will be from FC. Go to
Oh.
whatever.
Okay, cutoff frequency to FL. Okay, I got it. Thank you.
Okay, now band pass filter record output. Pass frequency higher than F1, FL, or less and less than F high. That's what they're telling you. They get a bandwidth here. Okay? So they get a two cutoff, one FL, F low. Okay? This is the one. This is another one. Okay? And basically, they will be going down for minus 20 dB per decade. Same thing, like the other one. Okay? So, any frequency higher than F high, they will be in the stop band. Any frequency less than F low, they will be band right here. Okay? Pass band will be going from FL to F high.
And the bandwidth is in between, which is F high minus FL is BW.
Why? Bandwidth.
Right.
Any question on this thing? Filter it is not hard to do.
I have a question, Mr. Pham, here. So for the low pass and high pass, as far as connecting them to the circuit, does it matter if which one is to be in the input or the output?
Okay, you're going to make the band pass with a high pass, low pass, right?
Yes.
So you get a high pass first. Output high pass will be connected to the input of low pass.
Input high pass, input low pass. Okay.
Okay?
Okay. Thank you.
Inverting band pass filter. Okay? That they just give it to you. The circuitry. I have nothing to talking about this thing. Okay? Last one. Band stop filter or not filter. So basically this is easy to understand. They just opposite to the band pass. Okay? That means any frequency higher than F high will be pass. And any frequency less than F low to be pass. However, the frequency between F low and F high will be rejected. Okay? Okay, so basically on this one here, they just introduce to you a different filter. Okay? One filter section, two filter section. One filter section means one pole. Two will be two pole. Three will be three pole. And four will be four. Okay? And the best will be four. The thing is, this is the best one. Why they will be the best one? The thing is, they will be narrow. Okay? The bandwidth here will be small. That's what they want. Why they don't want one filter section?
Too much noise.
Yeah, the thing is, the channel, that's really, really high open, wide open. So easy to get the noise. Okay? Also in here, they're just telling you different type filter from different engineer. First thing is you get Jabberjee, elliptical, Butterworth or Best-Fair. The only thing they show up here, which one do you think is the good one for the filter? Okay, you can see the ripple. Ripple in the band, that means you get a noise in the band.
The best cell.
Yeah, the good one will be first thing is they try to close into ideal. That means they close to in here. Okay? However, they have to be less noise. So the first one elliptical, not good, right? The thing is they get too much noise. Okay? And the next thing is Butterworth. Butterworth will be okay. The thing is, on the mid-range, they have a no noise. Okay? However, they still not a good one. Which one is a good one?
The Butterworth make you have a bigger bandwidth. And the best cell has a better?
Best cell will be better than Butterworth. They don't have any ripple, any noise in the pattern here.
Is,
However,
excuse me,
yeah,
is Bessel considered high frequency?
I know who care high frequency or low.
Well, it's faster, isn't it?
Yeah, with high frequency for sure they will be fast. However, on this display they just show you which filter you think good. So the filter is good, they're not supposed to get the ripple in the pass band. And
With-
also they try to close to the ideal as much as they can. So on this here, you don't care about that right here, and electrical they get a big noise. Only Butterworth and the best cell. But Butterworth and the best cell the same, they not get any ripple in the pass band. However, best cell get a better cutoff. Okay?
Because you want like a smaller bandwidth, is that correct?
Right.
Mr. Friend,
Yeah.
other than filter, what component is the primary factor to keep a Bessel signal as clean as possible?
Oh, that's the same thing. That means you have to looking into the best cell circuitry compared to the Butterworth circuit. Then
It- Isn't it the fill time of a capacitor that determines that ripple effect?
no, they have to be different. For somehow. I mean, you can get the Butterworth low pass filter, and also you can get the best cell circuitry, and you can compare to see what the difference.
Thank you.
One question, Mr. Pham. But here you're talking about active filters, so that mean it's necessary to use, for instance, an active component like an operation amplifier to build that filter?
Exactly. You can learn filter the same thing in the AC circuit.
Okay, got it. One more question. Given there is difference in the performance among these different filters, there is a difference also in the price to build a vessel in comparison to lower quality of these filters.
I'm not quite following
In short, build a vessel filter that is the performance is superior to the other ones is more expensive.
No, I have no idea.
Okay, thank you.
You can take a two circuitry for Butterworth and a best cell to find out. Okay, so that's just a summarize for you guys everything. Okay? Let's see. This is a page you have to go through. Band pass filter and home calculation here. Okay, they get a bandwidth. Okay, bandwidth and also equal F C2 minus C1. Okay, and you can use F0. What's the name for F0 here?
Center frequency.
Yeah, you can say center frequency. FC1 just cut off lower, cut off FC2 higher cut off. Okay? That's very good. And also they get Q. Q means quality of the filter. They will be F0 divided to bandwidth. Okay? Okay, let's see. This one just is not filter, nothing. Okay? So basically, remember, we only get 4 different types of the filter. Low pass, high pass, band stop filter. What I expect you to memorize. When they're giving you the output, you're able to tell what they did here, for example. Okay? They can tell you, asking you what they did here. And you have to say this is the output of the band pass filter. Okay? If they want the bandwidth, then the bandwidth will be equal to FC 2 minus FC1. Okay? If they want to calculate the quality Q, that means how good the filter should be, equal to F0 divided by the bandwidth. Okay? Any question? Anything? Okay, if it's not, make sure you download the JSPad for lecture today and tomorrow. Okay? You know, you have to go into the handout, download the JPEG of the phone 2020. So we will go into that.
Is the filter still in the handout?
Yeah, still. That means you download active filter, and also you have to download the JPEG. You must get that thing, okay?
And that's on the digital handouts or what?
No, electronic lecture.
Okay. All right, I see it. Okay.
You get that?
Yeah.
That is on of the major in electronics we have to be covered. JPEG will be the last one. We still get something else to do, like comparator, okay, like differentiator, integrator, okay, but that's not a major.
So, Mr. Pham, the main difference is the bipolar junction transistor is current control, and the JFET is voltage control.
Yeah, we'll see.
Okay.
Okay, now JFET is a junction field effect transistor. It's a type of FET that operates with a reverse bias on the PN junction to control the current. Okay, depending on the structure, they can be either in channel or P channel. Now you see on this thing here. Okay, they show you this is N channel. Okay, N channel that means that's the P side, and in here they will be N side. Okay, and the first one to go here is the gray, and this will be the gate, and this will be the source. Okay, for N channel, and the P channel, and you can see they will be P inside. Okay, and N on the other. And they given to you the symbol here. That will be N channel, and that will be P channel. What's the difference?
The arrow pointing out on the P channel.
You can see right here, arrow.
It's either arrow in or arrow out.
Arrow in, and arrow out, P channel. And also they get three terminals, drain, gate, and the source. Okay? Only thing is make sure you understand when you see in the symbol, you know what is JFET. However, they will be N channel or P channel. Get that?
Yes, sir.
What?
Yes, sir.
Now, two main type of FET. JFET is a junction field effect transistor. MOSFET, that we call a metal oxide semiconductor field effect transistor. In the MOSFET, we can get a D MOSFET or the E MOSFET. D MOSFET means depletion MOSFET, and E will be enhancement. Okay, similarity. They can be using as an amplifier, a switching device, and an impedance matching circuit. That's the application for the JFET. Different.
I have a question.
Yeah.
Is the similarity between what? A transistor and a JFET? With whom it is compared?
You mean the simulation of what?
No, you said similarities. Similarities with what? Which other electronics components? Is it a transistor or what?
Transistor. That's the transistor.
I think, Mr. Pham, what the thing is one transistor is bipolar junction, which is emitter base collector, and the other one is a FET, which is drain source gate, and one is current control, and the other one is voltage control.
Exactly.
Okay, thank you.
We already get the bipolar. Okay? They can get NPN and PNP. In the JFET, they say they get the N channel or P channel. Okay? On the bipolar, you get the base collector emitter. On the JFET, you get the drain, gate, and the source. That is the same thing. Okay? Now they're talking about difference between JFET and the bipolar. FET are voltage controller device. Why the bipolar is a current controller device. That's a very important. You must be memorized. They will be asking you. FET also have a higher input impedance, but bipolar have a higher gain. You want more gain, you're using bipolar. Okay? But you want to deal with the impedance, that the FET will be the good one. FET are less sensitive to temperature variation and more easily integrated on the IC. That means easy to build. Okay? FET are less sensitive to temperature variation. Okay? And easy to build. And FET also generate more static sensitive than the bipolar.
Hey, Mr. Pham, at the top of that handout there, you got MOSFET. The MOSFET, you can't be handling that with your hands. You got to have a special tool, right?
Right, we're talking about later.
Okay. All right.
Right now, we're talking about FET. They will be very sensitive. Okay?
I have a question.
Yeah.
So the last point of the differences is FET are also generally more static sensitive. What does that mean, static sensitive?
That means you cannot handling by hand.
Static electricity, basically.
Right. Your body get a more electric. That will be cooked the IC.
Inside the factory, you gotta wear a special suit, right?
Right. Whenever you get a job, that is the first thing they training for you. How to handle your IC. Okay, bipolar, okay, you can hold the NP, no big deal. But the fat have to be careful. Same thing like the bipolar. They fat before they can using, like the amplifier. They have to get the DC bias. That means you get a BDC to make the fat working first. Okay? VDD. You can see VDD right here. On the bipolar will be VCC. You need that power supply. Okay? And also, you get another power supply. VGG. Okay, negative. Okay? VDD provide a drain to the source voltage and supply current from the drain to the source. VGG set the reverse bias voltage between the gate and the source. The JFET is always operate with the gate source PN junction in the reverse bias. Okay? On the bipolar, they in forward bias. Now, try to see this picture here to see what the difference. If you're looking on the first one here, okay, on this one, when they measure at the gate, you can see VGS will be more negative, okay, and current on the ID, you can see here, that is the current ID, okay, and now, if you see on this one here, VGS going low negative, and now ID will be more. Okay? That only tell you this thing. This is what they call a channel. Okay? More electron that are inside, more electron moving, you get more current. So if I'm looking on this one compared to this one, I see this will be more current. Okay? So that's why they're using the meter to monitor. You get very high negative voltage. That means the current will be lower. And if you get less than negative, current will be more. That means the channel here, they widen. Okay? That's how the current will be flowing through the current ID. And also that will be given to you, okay? The IC for the JFET, okay? Let's see, what else? Now, see this one. You can see on this one here, when they draw the power with the arrow here, that means they can vary the voltage. So the negative voltage going down, keep going, okay? And that current will be increased. So the channel will be bigger, okay? More electron will be moving from the drain to the source. Okay? Now, we'll see this thing. This is a JFET. They connect to the route here. Okay, gate connect to the route. Okay, and you get a VDD. They changing the VDD. That means you changing the current ID. Okay, and on this one here, the 0 here, at the beginning 0, okay? And the current ID, this stands for ID, okay? ID going up, that means they change the VDD to make the current here go up, okay? They keep going up to the point B right here. And now they not up anymore, okay? In this case, they will be rounded at the gate. That means they say VGF equals 0, okay? So when they go up to this point right here, then they get the VGF now equals 0, and the voltage VDF right here equals VP. What is VP? VP they call a ping off voltage. What is a ping off voltage? Ping off voltage, that means at that voltage the current will be constant, no more changing, okay? And that's what they call a ID at S right here. So now, what is the ID at S? What is
Inch of voltage.
that? Means the maximum current. However, that maximum current only happens with VGS equals 0. Okay? That's what they call IDSS. So, now you can see, if they changing VD, okay, the first one less than VD less than VP, less here. This time they call a ohmic region. What that mean, ohmic region?
The JFET operates like a resistor.
Exactly. That means when the VD is less than VP, then the JFET working like resistor. Okay? However, when the VDS higher than VP, ping off voltage, and now the current will be constant, and that equals IDSF. And that only happens with the VGF equals 0, okay? And if they increase the VDS up to this point here, they will be break down, okay? So basically, JFET will be working like if the VDS less than VP, they can working like resistor. However, higher than VP and less than a maximum, VDS maximum in here. VDS max. Okay, they will be working like a current source, and that current will be equal ID at S. And after that, they get the breakdown. We don't deal with that. That will be cooked at JFET. Okay? So basically, JFET, they can using at a current source, constant current. And that will be ID at that. Or they can be using at the resistor. Like exactly in the bipolar, they can working like be saturation, or they can be working at the amplifier. Okay? Any question on that one? Oh, you don't know how to act.
Yes.
Okay, now This thing. The maximum drain current out of the FET occur when the gate source voltage is zero, VGS. Okay? Maximum drain current, okay, out of the FET occur when gate source voltage is zero. That only telling you VGS equal zero. Okay? Second thing, the drain current is almost constant in the region between VP and VDS max. What is VP?
Pinch off voltage.
Right. That means you must be memorized. Pinch off voltage. Okay? If the drain voltage is too large, the FET will be breakdown. The FET act like current source when it is operating along the almost horizontal part of the drain curve between VP and the maximum of VDS, like we just explained to you. Okay? From VP to V maximum, VDS maximum, they working like a current source, and the current will be equal IDSS.
Mr. Pham, a question.
Yeah.
Which two voltage? I know it's the pinch-off voltage and another voltage. They're equal in magnitude, but one has a different sign.
That will be, let's see. We'll be talking about that, okay, quickly.
In other words, the pinch-off voltage and this voltage I can't think of, they have the same magnitude, but a different sign, like a minus sign.
Yeah, but VGS off. Okay?
Okay.
Get later. VGS off. They will be the same value with the VP,
Okay.
but they will be opposite. Okay?
Okay, thank you.
Yeah. Between ping off and the breakdown, the FET act like current source with the value of IDSS. Remember, you must be reading this over and over. I combine too many different textbooks to summarize what really you need to memorize only. Okay? The minimum voltage VP equal a ping off voltage. Okay? IDSS stands for the current from the drain to the source with the shortest gate across the gate. VGS equals zero. That's what I will be asking you all the time. What is IDSS? Okay? IDSS. That means
Drain the source with the gates are shorted.
with the shortest gate. That means the gate will be short to round. Or mixed region. The almost vertical part of the drain curve is called mixed region. That's equivalent to the saturation region in the bipolar transistor. Cut-off voltage. The value of VGS that make ID approximately zero is the cut-off voltage, VGS off. Okay, so now we have to get one more. What is the VGS off? That means at that voltage, the ID current is zero. Okay? Comparison of ping off and cut off. VP is the value of VDS, at which the drain current become constant and always measure at VGS equal 0. VGS of and VP are always equal in magnitude but opposite in size. Okay? VGS of equal minus and VP equal positive. Now, data sheet usually will give it to you VGS of or VP, but not both. If you know VP, you know VGS of. Okay? Or you know VGS of, then you know VP. Normally, on the data sheet, they given you IDSS. They given you VGS of or VP. Now, only see this one here. VGS control ID. Okay, if you look in here, you can see that is VGS. Okay? On the bipolar, this will be IB. So that's why bipolar will be a current controller. Now on the JFET, you change the VGS, you change the current ID. Okay? For example, you get a point in here. What are VGS equal?
-2.
Minus 2 volt. If you want the ID, you go to the left here. That will be ID. So basically, VGS control the ID. So that's why JFET is a voltage controller device. Okay? And now, when you go up to this point right here, you going down, you can get VP. VP equal 5 volts. That means at that 5 volt, the current now they will be equal IDSS. That's a constant right here. Okay? And make sure you have to understand VGS equal 0. Okay, so the question is what is the IDSS? Okay, the answer will be IDSS is the maximum current. Okay, at VGS equal 0. Or they can say VGS is shortened. Okay, so any question on this picture here?
Is any component greater than 5 volts? Are there other components?
Now, that means at the 5 volt, then the current ID will be equal IDSS. They start less than 5 volt, they will be in the ohmic region. Okay, let's see. On this thing here, it says JFET cutoff voltage. If you're looking on the picture here, you can see the channel. No more, right? This electron on this side cannot go to the other side. The thing is, P side is too big, okay? So that will be telling you what the current ID.
Zero.
Meter shows you 0 amp. So when the current ID equals 0 amp and the VGS now be VGS off, no more electron moving. So that's why no more current. Okay? So what they said right here, at the cutoff, ID equals 0. And the VGS now will be equal VGS off. Any question? This normally the picture now, you are looking in a display will be bigger, right? Bigger like in the past. The display on the screen.
Yes, correct.
The thing is, I tried to set it up the maximum display, okay? So that's why they make it bigger. Thing is, last time I see Kuma told me what is in the iPad to picture guy. So that's why I'm not using the desktop. Okay? Hopefully that can help your guys to easily understand it. Now, the basic operation of the P channel. So now you can see what the difference. P channel and the arrow will be coming out. However, VDD now will be negative. And the VGG now will be positive. That's only the difference. Okay? They will be working the same. However, you can see the power supply will be different. Okay, yeah. Listen. Okay, now, example. For the test circuit show, they given the UVZ of minus 4 volts and IDSS equal 12 milliamp. They want to know the minimum value of VDD required to put the device in the constant current area of operation. Can you do it? Now, like we already telling you, this is ID. That is VDS. And you already saw this one that are this way. Okay? What voltage here?
VP.
Perfect. VP. What is the current here?
IDSS.
Right, very good.
IDSS 0.
IDSS. And the VGS will be equal 0, right?
Yes.
And this will be the breakdown right here. We don't care. This is a constant right here. That's what they're talking about, constant current. That means in this area. So now they don't give it to you VDD. They're asking VDD. So you can see you can get D right here, F right here, get right here. Okay? So you can see VDD I can telling you VDD. That means the voltage drop across RD and DS. Okay? So VDD, they will be equal I D times R D, and you adding. That means the voltage drop here, adding the voltage here. VDS. Okay? Now, VRD. Can you calculate the VRD?
At 6.72, if we're using the value of IDSS as ID.
Yeah. The thing is, they want the current here to be how many? 12, right?
Yes.
So you get a 12 milliamp, you adding to times the 0.560. That means you can get the VRD. Okay? 12 times 0.56. And then you have to get another one. Okay? VDS. What the VDS equal? That means VDS will be equal, let's see, minimum value, okay, of the VDS, you make it to be constant. That means VDS have to be equal VP. That means right here. Okay, minimum. What is the VP?
Central.
That means they will be equal to the VGS up, but they will be okay
Positive.
positive for both. Okay, now you calculate to tell me what is the VDD equal. First thing you need to calculate the ID times RD.
So is it 10.72 volts?
Perfect. Answer will be 10.7 volts. Okay? you calculate the VRD and you adding to the minimum, okay, required to put a divide into the constant. You can see when you read it right here. Minimum value of VDD. Minimum to put it into the constant. That must be VP. You understand now? Or still? Okay, let's see. Nice. They fed transfer characteristic curve for N channel. Okay, so basically this stands for ID. This stands for VGS. Okay, now this point here, what ID equal?
0.
0. Okay, ID equal 0 and VGS will be VGS off. Okay, and another point right here, what VGS?
VGS is 0.
VGS 0. So that's what they call a IDSS. Okay? They say right here, ID equal 0, then VGS equal VGS off. Or ID equal IDSS, and then VGS have to be equal 0. So that is the transfer between VGS, okay, and ID. Now, on that one, they display both. One for VGS 0, minus 1, minus 2, minus 3. And the other one, they will be display the curve, okay, for the ID and VGS. So, this curve here will be calculated by this formula here. This is a formula to calculate the ID at any point. Any point here, Q point. Okay, any point. You want to calculate using ID equal IDSS. Times 1 minus VGS divided to VGS of square. Okay, that's only the formula to using calculate the ID. Okay, and in here, for example, they given you VGS equal minus 2 volts. Also, they can telling you what the current ID equal will be 4.32. And if you going down, you can get VGS equals minus 2 volts. Okay? So we try to get to this example. We quit and continue tomorrow. Now, Paxo data sheet of QN5459, they said, indicate that typical IDSS equal 9 milliamps, VGS off equal minus 8 volts. Using this value, they determine the drain current ID. First thing for VGS equal 0, VGS equal 1, and VGS equal minus 4. Calculate that to get the right answer, then we can quit. Okay, so again, I given you the formula to calculate ID.
The first one is 9 volts. Or I'm sorry, 9 milliamps.
VGS equal 0. Okay? You get on this one, right?
Yes, sir. I got 9.
Perfect. The thing is, ID equal IDSS equal none. You know why?
I think so.
But the thing do you know why they ID equal 9 milliamp?
Because of the formula, because you're using IDSS times 1 minus VGS.
Yeah, I understand what you say. ID, right? Equal IDSS, right? 1 minus VGS divided VGS off.
Yes, sir. Perfect.
Great. However, we don't need that one for the number A. Why?
ID is max at IDSS when VGS is used.
Because VGS is 0. VGS is 0.
On the number A, we don't need the formula.
Right.
VGS
VGS is 0, so IDSS will be
and
9.
ID equal IDSS.
IDSS.
Okay. Calculate number 2. Then you must be using the formula.
7.875 milliamps.
Oh. It's not quite the mine. Well, get the answer.
I got 6.89.
Well, get the right answer.
50-50.
On that one, ID equal 6.89.
Yeah.
Okay, make sure everyone try to do it, okay? You want to be a technician, that's a very, very neat to understand it.
Wait. IDSS is 9.
And we get the last one.
1 minus negative 1
4.5.
divided by negative 8. What am I doing wrong there? Oh,
What they want?
square. Oh.
I got negative.
9 times. Son of a bitch, I forgot the squared. 9 parentheses.
I got negative 2.241.
1 minus
that's all we
negative
want.
4 divided by negative 8.
You're using for number C. ID equal 2.25, right?
That's 9.
Yes.
Perfect. Need the time to read it again, okay? Tomorrow will be more, and a little, look like will be a little harder. Anything confusing, not quite follow it, just let me know. We
Hey,
can,
Mr. Pham, on
Yeah.
this one right here, the VGS off in the formula, would that be 0?
what do you mean, it off? In
In-
here, it's
In the formula where it's 1 minus VGS over VGS off, is the denominator VGS off? I'm asking you, is it 0?
No, which one? You're asking about number A, B, C.
Number C, where you use the formula.
A, VGS off equal minus 8 volts.
It's up in the example.
Oh, yeah. I missed that. I'm sorry. That's why.
That means minus 4 divided to minus 8.
So because minus is a plus, and
Right.
VGS is 1, so the reciprocal of 8.
Yes, that means you have to apply it to the formula ID.
Minus 1, yeah, times IDSS.
IDSS times 1.
Yeah, okay, yeah, I got it. Thank you.
Okay. Okay, any question?
We're going to talk about what or how these things fail, what it looks like when it fails later.
What fell?
The Fed or the
You talking about the technical,
Transit.
right?
what was that?
Get a question about what? Is it a D-Lab or what?
Maybe. We had the other examples of what happens when the resistor fails or
What the?
other components fail.
I think he means, are we gonna learn about troubleshooting the JFAT?
Yeah.
Anywhere, anything, have to learn about how to troubleshoot it.
Eventually.
So that's why I try to give you measure. You must know before you're able to troubleshoot it. You don't know how they work, then you cannot troubleshoot it.
You have a procedure point to point with the DM in order to determine.
That means this time we can do a good job. The thing is, next week, almost done everything on the lecture. Then the rest up to the end of the January. We have to deal with the circuitry. It's not working. What can you do?
Okay.
Hey, Mr. Pham, I got a question. So at the top of this example, it says VGS off is equal to minus 8 volts. And I know you didn't ask for it. So that means the pinch off voltage is plus 8, correct?
Yeah, VP.
Okay, yeah, so VP is plus 8.
Right.
Okay, thank you.
At all. Okay, make sure you guys read it. Tomorrow I asking you. Okay? And you have to answer me. Like I asking you what the IDSS, how to get the calculate the ID. IDSS times 1 minus VGS over VGS off.
50-50.
Okay?
All right, thank you, Mr. Pham.
Yeah, good night.
Good night.
Thank you.
Welcome.
Awesome.
Thank you.
You're welcome. Bye.
The